What if you could power your phone with a battery that stretches like skin? Or fuel your car with a liquid made directly from sunlight and water? This isn't science fiction. It's a field of engineering where the blueprints come from the oldest designer on the planet, nature itself. Welcome to Fun Facts Online. Today we're exploring bio-inspired engineering, a revolutionary approach where scientists are looking to the living world to solve our biggest challenges, from sustainable energy to advanced medicine. For billions of years, evolution has been running R&D, perfecting designs of incredible efficiency. Now, using advanced tools like nanotechnology and genetic sequencing, we are finally learning to read nature's language and apply its principles. This isn't just about copying the shape of a whale's fin for a turbine blade, it's about understanding the fundamental physics and chemistry at play. A gecko's foot isn't just sticky. It uses van der Waals forces through millions of microscopic hairs. A butterfly's wing creates vibrant color not with pigment, but with light interacting nanostructures. By abstracting these deep principles, we can move beyond the heat, beat, and treat industrial models of the past and build a more sustainable future. Two of the most exciting frontiers in this field are artificial photosynthesis, which aims to harvest sunlight like a plant, and soft, flexible batteries inspired by biological tissue. Let's start with the artificial leaf. Perhaps no natural process is more vital than photosynthesis. It's the solar-powered engine that turns water, carbon dioxide, and sunlight into the chemical energy that sustains almost all life. For decades, scientists have dreamed of creating an artificial version to produce a clean, storable fuel. This is a massive leap beyond typical solar panels. Instead of generating electricity that has to be used immediately or stored in a bulky battery, artificial photosynthesis creates a stable chemical fuel, like hydrogen gas or methanol. You could literally bottle sunshine for later use. To achieve this, scientists are deconstructing how a real leaf works and building artificial components to replicate its three core functions. First is light harvesting. In a plant, pigments like chlorophyll absorb photons. Artificial systems use materials like semiconductors or synthetic dyes to do the same job. The second step is charge separation. When light energy is absorbed, it excites electrons, creating a separation of positive and negative charges that gets the energy flowing. Finally, and most importantly, is catalysis. These separated charges drive chemical reactions. Specifically, they power a process called water splitting. The positive charges oxidize water molecules, producing oxygen gas, protons, and electrons. Those protons and electrons can then be recombined to create clean hydrogen fuel, or used to reduce CO2 into other useful hydrocarbon fuels. The true genius of a plant leaf, however, is how it integrates all these steps into one compact, efficient structure. A leaf's broad, flat shape maximizes sun exposure. A network of veins transports water, while microscopic pores called stomata handle gas exchange. Scientists are drawing directly from this architecture. In one incredible experiment, researchers in China took a real leaf from an anemone vitifolia plant and used it as a template. They infiltrated its intricate vascular network with titanium dioxide, a well-known photocatalyst. After burning away the original organic matter, they were left with a perfect ceramic replica of the leaf's internal structure. This biotemplated material was 8 times more effective at producing hydrogen than an unstructured lump of the same catalyst, proving the immense value of the leaf's natural design. At the heart of these artificial leaves are advanced materials. The most common approach is a photoelectrochemical, or PEC cell. This is essentially a semiconductor electrode immersed in water. When sunlight hits it, the water-splitting reaction begins. Researchers are constantly testing new materials for these electrodes, like bismuth vanadate and copper chalcopyrites, searching for the perfect combination of efficiency, stability, and low cost. They are also developing bio-inspired catalysts that mimic the active sites of the natural enzymes plants use. For example, molecules called porphyrins which are structurally similar to the core of chlorophyll, are being used to drive the reactions that turn CO2 into useful chemicals. Scientists are even building in self-healing capabilities, creating materials that can repair themselves from corrosion, a major challenge for any device that has to sit in water for years on end. While the efficiency of artificial leaves still needs to improve to become commercially viable, the target is about 10% solar-to-fuel efficiency. The progress is staggering. We are getting closer to a truly sustainable carbon-neutral energy cycle, turning sunlight, water, and our excess CO2 into the fuels of the future. Now let's shift from making energy to storing it. Just as the leaf inspires energy conversion, the soft, flexible nature of biological tissue is inspiring a revolution in energy storage. The rigid, blocky batteries in our phones and electric cars are completely mismatched for the next wave of technology: wearable sensors, soft robotics, and implantable medical devices. For these, we need batteries that can bend, stretch, and conform to complex shapes, batteries that act less like a brick and more like skin. Enter the Toothpaste-Like battery, a groundbreaking innovation from researchers at Linköping University in Sweden. It gets its name from its core components, which are in a fluid, paste-like state. This allows the battery to be shaped, stretched, and even 3D printed. Previous attempts at flexible batteries often just put rigid materials into a bendy, accordion-like structure. But that's a superficial fix. The Linköping team went deeper, changing the fundamental nature of the battery itself. They created what they call redox active electrofluids. Essentially, they turned the solid electrodes of a conventional battery into a viscous liquid. This electrofluid is made of a few key ingredients. The active material consists of conjugated polymers, which are plastics that can conduct electricity. To get the right, paste-like consistency, they mixed these polymers with lignin. Lignin is the natural polymer that gives wood its rigidity and is a massive waste byproduct of the paper industry. This brilliant choice makes the battery not only flexible, but also highly sustainable. The resulting battery behaves like a water balloon. It can be deformed and stretched to double its original length, while maintaining its electrical performance. The prototype has been recharged over 500 times, with minimal loss of capacity, showing it's durable as well as flexible. The applications for this are transformative. Imagine smart clothing with power sources woven directly into the fabric. Fitness trackers would just be part of your shirt. Implantable medical devices like pacemakers could use soft, biocompatible batteries that conform to the body, reducing discomfort. Soft robots, inspired by octopuses, could have power integrated directly into their flexible limbs. And because the material is a paste, it can be extruded through a 3D printer, allowing for custom-shaped batteries to be printed as part of a device's structure. Like the artificial leaf, the toothpaste battery is still in its early stages. Its voltage is currently lower than a standard AA battery, but researchers are already working on incorporating materials like zinc or manganese to boost its power output while retaining its unique flexibility. From an artificial leaf that turns sunlight into fuel to a battery with the consistency of toothpaste, bio-inspired engineering is changing how we solve problems. By studying nature's 3.8 billion-year legacy, we are finding paths to a future that is not only more advanced, but profoundly more sustainable and harmonious with the world around us. The most innovative solutions are not always invented from scratch. They are discovered in the elegant, time-tested designs of the natural world. Thanks for tuning in to G Fun Facts Online.